Today we're going to talk about the Grand Unified File Index. It's sort of a solution we have to our current metadata challenges and the metadata challenges we see going forward. With that, quickly acknowledge people in the audience and colleagues back at home that have contributed content, whether it's code, slides, diagrams, things like that. Okay, so just brief rundown of what I'll talk about today. We'll go into a little bit of detail about HPC at LANL. Hopefully you were able to attend Brad's talk yesterday. You would have gotten a much deeper look into what the science actually looks like. I'll sort of just highlight it as a systems point of view. And then we'll talk about the guts of GUFI in terms of deployment, performance, and where we're going ahead. Okay, so HPC at LANL. We've been supporting weapons computing for a very, very long time. All of this physics that goes on when these simulations can range from testing stability to material decomposition, defects, things like this. And these are long-running simulations. Long-running meaning months. I think our longest is 7 to 8 months. And big means 80% of a machine. So our current machine is Trinity. It has 20,000 nodes. So a job running on 12,000 to 15,000 nodes for 8 months. And as Brad alluded to yesterday, obviously you have component failures and job failures during those 8 months. So what our users do is they practice defensive I/O. In terms of supporting the defensive I/O, we don't want to spend time doing that I/O. That I/O is preventing science from getting done. So one of our main challenges for a long time was how can we quickly get this data out of memory into a storage system and let the scientists get back to doing the real computing. Okay, so as we move into the future, here are our last 3 iterations of machines that have been deployed. IBM Roadrunner there on the far right, all the way up to the current generation of Trinity. We're always trying to enable science, right? So oftentimes this means bigger computers. That can be node count, that can be memory. Oftentimes it just means more efficient computers, getting more science per something, whether it's per watt, per dollar, however you think about that. And that oftentimes means advancing a capability, right? So with Trinity, we introduced Knights Landing processors. It was mixed in with some Haswell processors. And then it was the introduction of the burst buffer, which is a solution to our getting the data out of memory into a storage system quickly problem. Okay, so here's what a general reflection of what's on our data center floor looks like. On the right-hand side there, you see that those are the compute clusters. We have several smallish clusters. Those are what we call commodity technology systems. Those are sort of off-the-shelf systems that an integrator provides for us. Those are relatively small clusters. And then at any given time, we usually have one premier system. Those are the supercomputers you hear about in the news. Right now, that is Trinity. Sometimes these can overlap with one another. While one is being deployed, one will be being taken off the floor. So Trinity also introduced the burst buffer. I talked about that. One thing to note is oftentimes when labs quote or other sites quote their performance, that calculation is done based on a theoretical operation. The measured performance of Trinity is 20 petaflops. Not that HPL is a good representation of efficiency or performance anyway, but I just wanted to be blunt about that. Okay, but I'm here to talk about storage. So everything else, storage from here on out. So our highest tier is what we call Scratch. This is where users interact with the data in the hottest form. So they realize that data does not live here forever. The residence is weeks, maybe a month. These systems are really designed for high bandwidth. That's the initial target. When we think about buying these systems, it's dollars per gigabyte per second. We have over 100 petabytes of this Scratch type system across the data center. Today it's mostly lustre, but we do have things, like I said, the burst buffer is a Cray data warp solution. We have a very small NetApp Scratch pad for users to use. And when users interact with this data, the metadata tools that they use are normal GNU tools like find, LSDU, things like that. Some very savvy users will take advantage of a file system specific tools. Lustre has LFS find, for example, that has a little bit of an optimization in it. And then at the far extreme, some users will write a parallel app that can interact with metadata, but this is very infrequent. Okay, so the next tier down is campaign storage. This system is designed with capacity in mind. So data lives in this tier for the life of a campaign plus some overlap. This is maybe months. If you have consecutive campaigns, this can be a year. Today's iteration of the solution is SMR drives. I'm sure you've heard about MARFS. The solution to our campaign storage system today is built on MARFS. So the data is two-tiered erasure, it's checksum, it's very safe in this tier. So it's a POSIX-like interface where users can land their data so that way they can pare it down before it ever makes its way into the archive. When we buy these systems, we think of these systems in dollars per gigabyte. Tools that users use to interact with campaign storage are what we call parallel file tools, so PF tool. If you get into our GitHub, that's PF tool. There's also a fuse interface where users can use the normal tools like find. And with that being said, if you look here down at the very bottom, you'll see a little cloud there called RedCap. That is where users go to use these parallel tools to migrate data from, say, Scratch to Campaign, or from Campaign to the archive, or the reverse. Okay, so the archive is forever data. Once data lands in the archive, it's there forever. So anytime we upgrade the archive or migrate to a new solution, all that data has to come along with it. So we really, really want users to think about what they store here. We want to make sure that we're only storing the most important data here. The current solution to the archive is HPSS. The metadata system there is DB2. I don't know if probably familiar with DB2. So this is a really specialized tool set to interact with that metadata. PSI is a tool you can use to do that. There is a fuse interface, but most of the interaction comes from the specialized tool set. And we also have home and project space. This is your normal home and project workload, make files, source code, things like this, some small libraries. Again, tools here are find, ls, etc. Okay, so we have all these storage tiers. I mentioned that there are a few different tools that users use to interact with the metadata. But this model of users really explicitly defining what data is important and them knowing what data is important based on their science, it depends on them to know what they name their files, how important the files are, whether they've backed them up or not. It really depends on good naming and hierarchy. If a user doesn't have this, they may just back everything up, and then as a provider of a service, we are now migrating data that doesn't need to be stored forever, and it's a additive cost over the life of the lab. So essentially, we need better tools, especially as we move into bigger machines, which will generate more data, which is why we developed GUFI. So in our earliest discussions, we wanted to make sure that we covered every tier. We wanted one tool set for users to interact with instead of having to know multiple tool sets. And most importantly, we wanted this index to be shared across users and admins. Anytime you talk about sharing user and admin data, now you have to think about security, right? So this introduced security. If we only worried about admins, we sort of throw security away because all admins have access to all the data anyway. So that would have been the easy case. But bringing users in, we really had to make sure we took security seriously. In terms of update time, so we realized that our index won't be up to the second date. Every time a user modifies a file, we will not have that modified in our index. So there's a trade-off in how frequently we update our index versus our impact on the source file system. We want our source file systems to still be usable. We don't want our indexing capability to grind those to a halt. Obviously, we want to be performant, which means parallel. We would like to support extended attributes. So extended attributes today in our data set aren't widely used by users. The hope is that users will implement some sort of a tagging scheme where they can mark their data with interesting things interesting findings they have about their data, or sort of what campaign it came from, so that they can easily search this later. And we don't have thousands of engineers to work on a software set, so we really need to leverage existing technology that we could understand and use as building blocks. Okay, so the fundamental design of GUFI is we recreate the source file system directory tree structure onto a local file system. So we maintain all ownership, all permissions on the newly created tree. And so if you think about the security implications there, these are the exact same Unix permissions we trusted on a source file system, so it's perfectly fine to use them on our local index. And then, so like I said, we only have the directory structure. So what we do is we take all the file metadata, we shove that into an embedded database, one in every directory. Today that is SQLite. So all of your file information goes in this embedded database. So your name, your mode, your UID, your GID, all of that information gets stored into our SQLite databases. And we parallelize this using threads today. So if you had a working GUFI, this is exactly what it would look like. You can see that every directory has its database. Every database has 3 tables in it. First, the entries table. That's the most important table. That's where all of the file metadata lives. You can also have a directory, or you will have a directory summary table. It does exactly like what it sounds. It summarizes that level of the directory, that directory only, with things like this is the max size, this is the min size, things along those lines. And that optimizes your generalized queries. And then optionally, you can stick a tree summary table anywhere in the tree. What that will do is summarize the entire tree below you. So similar to the directory summary, it'll summarize everything below you up at your level. So today, it is all mostly C. I think we even have less C++ than this in our current generation of the code. So there's some benchmarks left in C++. There's a little bit of Python. I'll talk about that in a minute. But we're mostly C, and it's a pretty small code base. So very powerful for not a lot of code. OK, so as with any system, we would obviously need to evaluate what alternate approaches there were and alternative solutions. And the first one that comes to mind is you just flatten a namespace, right? That's the most efficient way to do this, the fastest way to do this. The considerations there are if you have to update that flattened namespace, especially with something that was renamed on high or moved on high, that becomes a lot of updates to a lot of records, right? And then more importantly for our implementation, implementing security for users and admins in a flattened namespace like this is very difficult. So sharing those two things is very hard, and there's definitely a performance hit to doing so. So then you might say, well, you can use your supercomputer and you don't have to create an index. You can just go ahead and walk that tree every day or every hour, however frequently you want to do that. But my short answer to that is it's a resource problem, right? We buy these supercomputers to get science done. We don't want to use our resources to walk the trees. Secondarily, we don't want to denial of service our own file systems, right? We want those to be up and available for the users to use. And then lastly, the users like the tools that they have. They like find, they like ls, things like this. OK, so we started off with this very powerful base code. We could implement very powerful queries. But when we started thinking about deploying this to actual users, we realized what I just said. They like to use find. They know the find options very well. So we decided that we wanted to provide a wrapper that would build queries based on the options that find can provide. So we're compatible with most. We've implemented a few of our own that make the find tool a little more powerful. But it's just a very simple user interface to do those simple queries that users are used to interacting with the file system. We have find, we have ls. We are implementing du right now. And like I said, this didn't require a ton of code rewriting. All we did was use Python to wrap and use our existing code. OK, so how do we interact with the source file systems? These are what we refer to as ingest tools. Today, we have a POSIX tree walk. That's all done. That's working. That's how we're deploying to users today. But file system-specific optimizations exist. Things like the GPFS fast inode scan, going into DB2 directly with HPSS, going directly to a server with Lustre. So we really want to leverage those when we can. This lowers the impact on the source file system and actually increases the speed in which we're able to index our data. And then lastly, we were going to implement the incremental capability. So instead of re-indexing the entire tree every time you go to index it, you can try to figure out what you think has changed and only update those changes in your index. So all software projects have bugs. We've been at bug fixes, stabilizing our releases. So we're finally using Git tagged releases. We're having far too frequent releases right now. We're sort of trying to get a better cadence, stabilize that a little bit. And we have Travis integration, auto builds for these 3 operating systems. I think I saw a patch that broke Mac this past week, so we'll make sure that Jason gets to fix that this week. Okay, so on the other side, users have their CLI tools, but for quick and early adoption, we figured let's give users graphical reports via a web interface. So at first, these were supposed to just be sort of common user reports that we'd expect users to want to see or admins to see. But it sort of grew into, let's give the users intuitive visualizations of their data. Let's let them see how they stack up against one another, how they stack up over time. And let's let them build queries using the interface. So it's very small, but here's a first crack at the web interface. You can see there on the far right, users can select things like which file system they want to query, or they can select all of them. They can filter on things like file name, type, size, UID, GID, all of the normal things. And then we also have query capabilities. So here, man, it's not showing up very good. So here, a user could select multiple options to basically build their query that gets kicked off and then the results returned. So this is the user interface. As an admin interface, what we really wanted to do was build a site that would expose our entire schema to an admin, so that an admin can go in and look at anything we've indexed and run queries against that and sort of build advanced queries. So we're working on that now. All right, so the first phase of user interaction is our web and CLI. Again, our target is to get early adoption and easily deployed. So on the far right there, you see what I've called cluster front ends. This is where users log into a particular cluster and interact with their jobs. They submit jobs, they check on the status of jobs, they compile their code, things like this. So they spend the bulk of their time in interactive mode on these cluster front ends. So instead of having them log into a different box to run their GUFI queries, we thought we'd allow remote queries to be run from these cluster front ends. So we just wrote a very thin GUFI client. All this does is use Python, Paramiko, and host-based authentication to kick off queries from the cluster front ends to our GUFI search box. And then further breaking down the barriers to adoption, we want to allow our user desktops to see our web interface. So that way they don't have to do X forwarding to a front end and run Firefox there or anything like that. So sort of just a bare bones, here's the quickest, easiest way to get this into the hands of the users so we can start getting feedback. Okay, here's the meat, performance. So our initial test setup, we're using a Dell server with an Epic in it. This is Naples. We've got about 0.5 terabyte of RAM. We're on a little bit of an old kernel. We realized that we need to test some new kernels to get some NVMe updates. Currently, we are using NVMe SSDs. All of these results are only using one NVMe SSD with one XFS file system on it. And so the NUMA, the complicated NUMA architecture of Naples could be impacting our results. We're aware of it. We're going to test on a newer AMD system and some Intel as well. So our earliest results weren't quite what we expected. In the best case, they were pretty good. In the worst case, it didn't seem like it was worth the work. So what we did is, as scientists and engineers, we took out our measuring sticks and our stopwatches, and we figured out that SQLite Open was slowing us down by quite a bit. So we wrote this benchmark. What this benchmark did was literally only open databases. This is 200,000 databases. So time there on the y-axis, we're scaling out threads going on the x-axis. So you can see the knee of that curve is pretty far down in the number of threads. I mean, at 4 threads, we're basically saturating the amount of opens that we can do. So clearly something was wrong here. The blue line is comparing to just the Unix open call. Yeah, so like I said, greater than 10x there. So none of us were exactly SQLite experts in terms of knowing the code in and out. So we all opened it up, took out the manuals, things like this. And we realized that SQLite protects you from yourself, and rightly so. Your database, you need to be consistent. But we have no need for multiple threads to ever access the same database. So we don't need these protections. So we went ahead and turned them off for our benchmark. And we see that threads now help us, and we're much closer to what the system calls look like. We have an idea on how to close this gap a little bit farther. I can talk about that towards the end of the talk. OK, so all these results are including the modifications to our SQLite our SQLite flags. So what we did is we took the most basic query. We started with the most basic query. As a user and an admin, show me all of the files that I have access to in this file system. So there on the right, that is the user query, on the left, admin query. And then obviously the goofy lines are the darker blue. So you can see this user has approximately 300,000 files, about 13,000 directories, and then the entire file system, there's about 13 million files, about 1.6 million directories. So in our user case, in Goofy, we're sub-second for these queries, so that's fantastic. We're about 68 times faster than the normal find command. When talking about files per second here, I guess it's important to note, when comparing Goofy to another file system, files per second is a good tool to use. But if you look onto our GitHub and our issues, or maybe some talks, you'll see that when we talk about Goofy performance, we're always analyzing directories per second. The basic unit of measurement in Goofy is a directory, because that is basically the smallest thing. There's one database per directory, so that's the smallest amount of work a thread can do. So internal performance, we generally talk about directories per second, but when comparing with file systems, files per second is correct. OK, so in the admin case, you can see that number there is about 34 minutes for the normal user interaction case. And we're at about 40 seconds in the Goofy case, so about 51 times faster. We're up in the 300,000 files per second. Another thing to note is the normal user interaction case is obviously dependent on the workload on that source file system at any given time. It is what users experience, so it's a good comparison here, but that is something to note. OK, so if we move on to lustre, those first two high-level columns are effectively the same test, except using our lustre trees, our scratch trees. And then this final big column here on the right is searching across both NFS and lustre at the same time. OK, so we see that our user in this lustre system has approximately 22 million files, 240,000 directories. We're about 8 minutes in the normal user case. We're down almost at 10 seconds in the Goofy case. So this is a pretty big speed up. You see that we're in the 1.5 million files per second case, 1 million files per second in this case, which is pretty fantastic. And then where it really gets powerful is you see in finding all the files in this system. We're at about 130 seconds, so about 2 minutes, a little over 2 minutes. And then in the normal case, 188 minutes. So our admins can no longer go get coffee while they run queries. They have to sit at their desk because the queries will come back quickly. And then the last thing here is finding both of all the files in both file systems. And in this very simple query case, yes, you could write 2 find commands that can do this exact same thing. But when you're talking about more advanced queries, then you have to sort of combine the output, post-process, and all of this, whereas with Goofy, you just get one set of output with all of the information that you asked for. And then something to note on the files per second in the lustre case. So you can go look at presentations from the lustre user group and other places. But I mean, lustre benchmark numbers for stat aren't really quite this good. There may be some hero runs that are about this good, but they take maybe 50 to 100 nodes to replicate this type of files per second performance. And if you think about running that type of a benchmark, the source file system's not really that usable. So these are pretty impressive numbers in our mind. OK, so quickly about index creation. So creating an index, this does not take into account the time to interact with the source file system. This is purely timing the Goofy index creation code. So we see that we're at about 40 seconds in the NFS case, just under 2.5 minutes with lustre. And then from indexing a production HPSS, we're just under 3 minutes. So these are all reasonable times to create an index. Okay, so if those performance results weren't good enough for us, we decided to squeeze out a little bit more. We realized that every single directory was a malloc call. This is because our work queue is based on directories. So we decided to try a thread-aware malloc, jemalloc, and it actually helped us quite a bit. So you can see in the smallest case, there wasn't much improvement, and based on the exact numbers, it went down a little bit, but that's likely due to noise. But I think my at least current theory is that if you look at the number of directories here, 13,000 isn't that many directories, so malloc may have not been hurting us this much in this case. Whereas if you look at the entire file system case, we have about a 42% speed up based on just switching out the malloc library. So we're now we're almost at 600,000 files per second from 300. So those exact same improvements to our lustre queries. So these results weren't quite as drastic as the NFS case, but each one is about 20%. We're almost at 2 million files per second here. You can see that we're down almost near 10 seconds for those user queries, which is great. Okay, so if we wanted even more performance, my colleagues came up with this really fantastic idea of what we call rollups. And if you can think about a rollup, it's similar to the flattened namespace approach that I discussed earlier, but it's sort of taking security into account of how you do those rollups. This is done post-process, so an index already has to exist and be created. All those tables have to exist, the directory structure, all of that. And the rules that we implemented don't allow every single rollup possibility, but it turns out that it's a pretty good chunk. You can see that in an NFS case, at a certain level of the tree, we're able to roll up about 60% of the directories at that level. So that's a pretty large reduction in the amount of directories that we have to process. And like I said earlier, when we're thinking about performance, it's in terms of directories per second. So if we reduce 90% of the directories in the tree, we can think of that as almost an order of magnitude speed up. So extrapolating from queries done on a small dev system, we have an expected speed up of about 5 to 10x, and I'll talk about those numbers on the next slide. I quickly wanted to review the rules that we've implemented. In the most basic case, you can think about if a user has allowed world to read and execute from a particular spot in the tree all the way down, that any user can access all of that data. So that is a valid rollup point. If a user group and world permissions are all the same from a particular spot in the tree all the way down, and the UIDs and GIDs are also the same, then you can roll those up. Similarly, if a user and group are all the same, and then the UID and GID down that tree are also the same, and there is no world read and execute at the top level, then you can roll up to that level. And then the last one, so you have the user permissions are the same all the way down the tree. UID is also the same. And then you're missing group and world read and execute at that top level. You can also roll those up. So based on that optimization, we expect that at the very, very bottom end, over user tools, NFS is likely going to be about 100 times faster. In our lustre case, we think that will be approximately 80 times faster, likely again much, much more once we actually benchmark this. And those are the user queries. So admin queries can be rolled up even farther because the admin queries we don't have the security issue. So we fully expect that all user queries become sub-second, even across multiple file systems. We fully expect all admin queries are in the minute range, hopefully under 2 minutes. Again, those are queries that can cross the span of the entire data center, all of our tiers that we talked about. Okay, so we want to squeeze more performance. We always want more performance. So a likely speed up we expect. We've dabbled with it a little bit and seen some strange results. But sharding. So sharding ideally offers us some sort of a free speed up. put more drives in, more file systems, we sort of get the capability to scale out. That does require code incorporation. We have to modify all of our tools to know how to deal with a sharding. Not a big heavy lift, but it is work to be done. File system comparison. So we've strictly been using XFS. We should likely explore other file systems, potentially user space file systems. And then the rollup integration. So today, the idea of the rollup does not modify any underlying concepts of GUFI. All of the schemas, all of the tables exist in basically the exact same way that they did before rollups existed. If you take that a step farther and really integrate it into the code and change some of the guts and depend on the rollup, we can likely see further improvements in the performance. OK, so SQLite open optimizations. So we had someone sort of look at what exactly open was doing in SQLite. It turns out there's 6 to 8 system calls for every SQLite open. Some of them are stat being called multiple times without saving a struct. So we think that we can remove 80% of those. Obviously, if we're going to remove system calls from SQLite open, we need to test and test and test. So that's sort of the mode we're in right now. And then our sort of next steps in analysis. I showed you the most basic case of queries, but I talked about very advanced capabilities in queries. So now that we're ironing out all of the performance in the base case, we really want to start running some of those more advanced queries using GUFI to analyze our trees. And sort of the low-hanging fruit there is analyzing our archive, which we think has a lot of empty directories at this point. So lastly, we would like to characterize GUFI in terms of building equations to analyze the cost of each type of work that GUFI does. So you can think of things like what the cost of operating on a directory is, similarly what the cost of an open is, queries, things like this. So that way when we think of other optimizations or we want to compare to other state-of-the-art tools, we can have a nice place to start with just a mathematical foundation. I finished a tiny bit early. Hopefully there's lots of questions. I guess I will comment on this. So GUFI did win an R&D 100 award last year. I'm very proud of that. And if you go, we're all open source. We take contributors, testers. If you want to just file bugs, we were happy with that. All of our research as part of our ultra-scale systems research center is there at that web link. And we have a nice joint effort working on efficient mission-centric computing. This is collaborations with vendors and things like that. So go to that website if you're interested in any of that. You can get in contact with us.